example is going to be primarily dependent upon two IPs. Okay, they are Xilinx inbuilt IPs, two IPs that are ILA and VIO. What do they stand for? Is ILA is integrated logic analyzer, to VIO is virtual input output, VIO and ILA. The way they are designed is such that they both can be accessed using JTAG. Okay. So, we do not need any additional peripherals in our design, but just JTAG. Okay. JTAG will help us do the transmission of data throughout. Okay. So, we will go ahead, we will look into ILA and VIO when we come to it, right. But to start off with, if you have already opened Vivado, create a block design. So, we will be working with IPs. Okay. You can just leave the name as design 1. So, once we have the binary counter added, okay. So, what we are going to do is we are going to increase the number of outputs for this binary counter. So, we have the binary counter output width decided as 16, rather we would make it 32. Output width is going to be 32 and we will add one more control signal, which is clock enable. The counter IP, I have increased the number of outputs that I am looking for and I have added a control signal, right. I have added control signal, which is clock enable. Okay. You can click OK. Sorry, 32. Go to the control signals. Control tab is there, no? So, add a control signal, control enable. In basic, the output width is 32. That runs up till 32 bit. Okay. And we have a control signal for that. Okay. So, the next thing is we will add something called as the ILA. ILA is integrated logic analyzer. Same thing again, add ILA. You can directly search for ILA. Under control, clock enable is there, no? That one you need to turn on. Next, add one more block, ILA. Sir, it is about analyzing a logic, it is not adding more logic. So, as we have discussed, ILA is integrated logic analyzer and it is designed in such a way that it can work through the JTAG itself. We do not need any additional components for it to work. There is no extra connections, there is no extra protocols that it is following. It is going through the JTAG cable that we already connected for power. So, I have the ILA and this is working through JTAG. Okay. The thing with ILA is that it is working in read only mode. You cannot send signal, you can only read signal. Okay. It is only for analyzing our logic. There is no recreating the logic or putting extra logic in. Okay. And it is always synchronous to the provided clock. Okay. If we have a clock in our design, it is always synchronous to the clock, right. So, we have added the ILA. So, let us do some customization here. I am using this ILA in a native mode, not AXI. So, we have the monitor type native and in probes, I am probing all the 32 bits of my counter. 32. Yeah, probe 0, the width of it is 32 bits. The next thing is we need to add the VIO, because we have a counter VIO, double click to add it. Okay. We have the VIO block, right. So, one primary thing that we need to understand while using VIO. So, we have added ILA, we have added VIO. We have already customized the ILA, now we will customize the VIO. Okay. Double tap to open the customization option. So, the thing about VIO is it is internal to our design. Okay. It is only existing inside our design, externally it is not there. So, what happens with the inputs and the outputs of our design is inverse to what is the input and output of VIO. Okay. So, in other words, if we are taking an output from the VIO, that becomes the input for our design. If we want to read the output of the design, that should be the input to the VIO, because it is virtually it is creating a loop. The output becomes the input, the output of the VIO becomes the input for the design. Logic analyzer is added. So we need to match the number of ports and the port width, okay, the width of each port. Okay. So the number of probes, right, the input probe count should be 32 because I am probing 32 bits of the counter from the output. Okay. The output probe for the VIO is going to be 1. Why is it 1? The output of the VIO is the input for our design, right. What is the input for our design? Clock enable, right. So clock enable is only 1 pin. So output probe for the VIO is going to be 1 probe. Okay. Once you have done this, you need to assign the depth. Okay. You can go into probe in. Okay, 1 second. Or you can do one more thing. You can go to general options. Input probe count can be 1, and the probe width can be 32. Right. The input of my design is only one signal, which is clock enable. So it should be 1, right. So only one signal is required. The 32 bits, yes, are there, but they are the input of VIO. Output 32 bits of my design are the input 32 bits for my VIO. Input of what? Input, output. Yes, they exist. There are 2 inputs, 2 outputs, right. So the output of my design, which is the counter, should be the input of my, right. So output is how much bit? Output of design. 32. So input of VIO should be 32. Input of design is how many bits? 1 bit. Clock enable. Design is counter. Counter needs clock enable, right. Only 1 bit. So how many bits of output should the VIO give, right. So here you have one clock, right. You have a clock enable signal. General options law, input can be 1. Input probe count 1. Can be 1. See, it depends. If you want to check every single signal separately, you can take it as 32. No problem. You have to make 32 different connections. That's all. Okay. If not, you can take one probe with the bit width of 32. General option can be 1 and the probe width can be 32. Or if you want to take each and every single signal separately, okay, you can give 32 bits of probes and you can attach it to every single signal as an output. That is also possible. So or else it can be the other way around, it can be 32 ports with 1 bit, that is also possible. We have added 3 components. One is a counter, ILA, VIO, right. So the advantage, one advantage with Vivado tool here is that you don't have to manually do any kind of connections. Some are required, but most are taken care by the tool. You have the designer assistance available here, right. At the very top, you have designer assist. Here, it will ask you what are the blocks that you want me to connect. It will not go ahead and do it on its own. It will ask me what are the signals that you want to connect, what are the blocks that you want me to consider. So right now, we can select everything. But if you have an option, if you want to do some manual connections by yourself, you can do it as well. Okay. You can just select everything and click OK. If I had already done, okay, I will just click Ctrl Z, undo that. Okay. If I had connected all the clocks, then it will take all the 3 clocks are same. But I haven't connected the clocks, I just left them open. So it considered 3 clocks to be provided for this particular design. Okay. So what if I just connect all the clocks and now run connection automation. Select everything, click OK. The clock wizard that is generating the clock, and we have the counter, ILA, VIO. Okay. But even when I run the connection automation, there is no connection between the VIO, ILA and the binary counter. It only added one single block, which is a clock wizard. Okay. So we need to make manual connections because the tool cannot confirm that all the 32-bit probes that I have given are connected to the output. It can be for something else. Okay. So if it is not sure about what these connections are, it will not touch them. So you can be sure that there will be no wrong connections. The output of the binary counter to the probe of ILA and to the input probe of VIO also. Okay. So the output of the counter should be connected to both the input probes, ILA probe and also the VIO probe. ILA, I'll just show you. So probe is only one. Probe width is 32. What you have done is you have done number of probes 32. Now one more connection is required, which is the output of the VIO is the input for my design. Output of VIO to clock enable. Okay. Once it is done, just to verify, we'll run connection automation again. Run connection automation, select everything, click OK. So all it is doing is it is giving ports for clock wizard. It will not consider them as one single clock, because you have 3 different wizards. It will give 3 different signals altogether. It can be set to a same frequency, but the thing is you will always have that as a 3 different clocks only, not a single clock, right? Even you can see here the output clock frequency is 100 megahertz, but underneath that you can add more clocks, right? But they are going to be different clocks. You can have same frequency but different clocks. See, optimization is getting done to convert a design that something the FPGA can understand. It is not changing our design. If I require 300 rupees, I need 300 rupee notes, not 100 rupee note 3 times, right? So if you have given 3 clock wizards, it will consider that you will require 3 clock wizards, it will give you 3 clock wizards. It will not say, okay, use this clock wizard 3 times. That is not possible. It's not customization. The customization is only happening, okay, 3 clock wizards are there. What is the MMCM or PLL that I have selected? Which one should I pick? And what is the clock routing that I should do? That is the only customization that it is doing. It's not changing anything else. It's not changing the design at the core. Everything is same. The only thing we need to understand is, once we have clock in 1 as system clock, right? System clock, it is going to be 100 megahertz, because the onboard frequency, onboard oscillator is working at 100 megahertz. So once we are done with this, we are almost done with our design. Okay. But the only problem that I have with this design is I cannot see the output anywhere. Other than virtually, I cannot see the output anywhere, right? So what do I need is, I need to add something in this design so that I can see the output physically. Okay. So what I will add is something called as a slice, SLICE, slice. This slice is going to be a simple in out. So once you have slice, once you have added slice, we need to customize it to pick out the output. Okay. So double click on it. So the D in width is going to be 32 bits, because my design output is 32. So I am taking all the 32 bits in, but I am only expecting a set of outputs to be shown. Okay. Only a set of outputs to be shown. So D in from, I will say 26 bit down to 23 bit. So my input is a 32 bit input, but I am only taking a part of my input as the output. It's just slicing my input with the number of bits that I have. I'll just click OK, done. So I'll just give the input connection, right? Input is connected to the output of my counter, 26 to 23, 26 down to 23, or you can give anything we can do. Yes, I have connected manually and I am making this external. D out, right click on D out, the pin D out, make external. D out, right click on D out, you will be able to see one option to make external. Because I am doing my design using IPs, okay, do I get the constraint file here? It doesn't do, but why doesn't it do? So we have said that we are taking 4 bits as output, but we never specified what our output peripheral is. Our output peripheral usually will be LED, right? But we haven't specified that. So once I am done with the design part, what I can do is, there is an option to regenerate layout. This just cleans up my design. Okay. There is an option called regenerate layout. Okay. And then I can validate my design. So I have done all the connections. Okay. And I need to verify if my design is functionally correct or not. So there is an option to validate design. Click on validate design, regenerate layout. There is a refresh, this thing is there, no button. regenerate layout, and once I am regenerating the layout, I can validate my design. So, this will tell me if my design is functionally well or not. Okay. So, once I have this, it is the same thing again, same process. I need to go for design wrapper, generate output products, right click on the design, right click on the design, generate output products, again out of context per IP block. Once the once the output products are generated, I can create a wrap. Okay. Once our wrapper is generated, we can go for run synthesis. So, once I have opened my synthesized design, what we are doing is we need to assign the pins that I am using. Okay. You will be able to see one clock. Okay, it's sometimes it is already assigned. Okay, if it is not, for ping Z2 board, the system clock is H16. H16 is the pin for system clock in ping Z2. Once you have assigned the clock, the next thing is going to be your output pins, D out 0, those are 4 pins, and your reset pin. Okay. So, what I will do here, the output pins, the LEDs, I will assign them to LEDs. Okay. I will just say LV CMOS 33 and I am giving all the LED values. LED values M14, M16, P14 and R14. Okay. So, you can, if you have any questions, you can directly do a small Google search, ping Z2 master XDC. Okay. You are in IO ports, right? IO ports tab, you need to assign system clock. If it is not, it is H16. You need to assign the D outs. D out 03 is going to be M14, 02 is N16, 01 is P14, 00 is R14. Okay. We are just assigning it to the LEDs. IO standard is LV CMOS 33. Similarly for reset pin as well. Okay. LV CMOS 33 and the pin number is M20. So, once we have assigned that, we can run implementation and bitstream. Open hardware manager, open target. Okay. I can connect my board, open target and I can dump the program. Dump on the board. Okay. So, what I will do, program device. Yesterday when we were dumping, we were only selecting one file, which is bitstream file, right. So, today we are giving two files. One is a bitstream file and the second is a probe file. Okay. So, if we are trying to debug, we need to add those probe files. The ILA is giving those probe files. Okay. So, the probe files are generated, the bitstream file is generated, both are being added and dumped onto the design. So, once you have dumped, this is what you will be seeing. You will be seeing the ILA window, integrated logic analyzer, and the VIO window. So, this is the ILA window and this is the VIO window. So, we are not able to see any pins inside the VIO window. We have added inputs and outputs, but we are not able to see because we need to add them again. So, click on the plus button, inside that you will be able to see the inputs and the outputs. The input is a single bit input, the output is going to be 32 bits, 31 down to 0. Okay. So, for the input, what I am going to do, instead of having it as a drop down menu, I will just switch it to toggle button. I can expand all the 32 bits. So, if I want to run the program on the board, if I want to run the counter on the board, okay, I can directly give an input from my laptop. If I turn it to 1, we can see that the counter is running. Okay. And we can also see the LEDs that we have assigned on the board running. So, we have taken a part of the output, put it on the LEDs. So, because we only have 4 LEDs here, I am running only 4 LEDs, right. If I want to check only 2, no, we can see it in the tool, we can see, yes, but here we only have option for 4. So, we are only seeing 4 outputs here. So, of those, the LEDs from 23 to 26 are assigned to the LEDs on board. I can trigger my ILA. So, once my counter is running, I can go to ILA. I have the trigger button here. Okay. If I run the trigger, so you will be able to see the output for my ILA. Okay. The output for my ILA is 1024 bits of data. Okay, 1024 clock cycles it is showing. So, if I zoom in here, you will be able to see my trigger is happening at 512. Okay. I am able to see 4, 5, 6, 7, 8 and so on. Okay. Each clock cycle the count is increasing and I am able to capture it for 1024. So, there are a few things that we need to understand at the core when we are working using Python on Zinc. Okay. So, the combination of Python and Zinc is called Pink. So, it has a specific framework and the framework is described as given here. Okay. So, we have the hardware design, we have the FPGA design done in Vivado as layer 0. Okay. The output of this is going to be a bit stream, we have already seen that. Okay. The next thing is a Linux kernel that is working. Okay. This is similar to our embedded system designs ELFI. Okay. But this particular driver, the Linux kernel, can be stored on an SD card. Okay. Rather than directly dumping, this can be stored on the SD card. Okay. And this particular Linux kernel is running the APIs based on Python. So, inside this Linux kernel, there are APIs based on Python. Okay. That includes all the Python libraries, the DMAs required for connections, the PLO overlays, the GPIOs, the interrupts, everything is available in the APIs. Okay. And based off of these APIs, we will be launching the application called as Jupyter Notebook. Okay. So, this is the structure that we will be following. So, on the board inside the SD card, we will be storing all of this in a particular format. Okay. The hardware bitstream files, the drivers that are required, the APIs inside those drivers and one application, or all of them are stored on the SD card and we will be booting the board from the SD card. Okay. Rather than using a JTAG to program it, we will be booting the board from the SD card and then programming it externally. Okay. So, the main thing here is adding something called as a bitstream file. Okay. So, what we are doing is we already know that the most important thing when working with FPGA is a bitstream file. Okay. So, we can have customized bitstream files. Okay. Based on our requirement, whatever the hardware is required, we can customize what is required in the bit file itself. Okay. So, once we customize that, we can export it and save it on the board. We have seen here the base layer is a bitstream, right. So, that bitstream can be loaded in our program and we can work on that particular bit file. Okay. So, it is called bit file overlays, okay, using overlays to input bit streams. Using Python, we have a wide range of flexibility to import packages. Okay. OpenCV can be done, Matplotlib, scikit-learn. Okay. Any of the available applications, even BioPython can also be included as a package and you can run on FPGA. So, there are multiple boards that support this particular programming methodology, the Ping methodology. There are multiple boards, Ping Z1, Z2, ZU, right, MPSOC boards 104, you have RFSOC 111, 4x2, all these boards do support Python productivity. Okay. The applications are limitless because wherever Python can be used, wherever Python can be accessed, wherever Python has already been used can be run on this. So, there is okay, one thing we need to understand is that okay, how are we running this on the Ping board is we are using the JTAG cable only for power and the data is getting transferred through the Ethernet cable. Okay. The data is getting transferred through the Ethernet cable. There is an image already burnt on the SD card. Okay. Where do we find that particular image? Is you can search for pink.io. There is a website called pink.io. This board, this particular page has all the information regarding the Pink. there is a set of boards and you can download all the board images right here. Okay. So Z2 is supported, Z1 is supported, ZU is supported, Kriya boards is supported, 104 RFSOC boards, 111, 208, all these boards support pink. Okay. You can download that particular pink image and you can burn it onto your SD card. Okay. Once you have done that, you need to make sure that the board can boot from the SD card, that is step 1. How do we do that? Is change the boot mode from JTAG to SD card. Okay. The jumper here right next to the HDMI, we need to switch it from JTAG to SD card. Okay. That is step 1. Step 2 is that we need to connect the board both with the USB cable and the Ethernet cable. Both are required because USB is giving power to the board, the Ethernet is transferring data. Okay. Once you have these connections done, you need to make sure that the board can be interfaced with your system. Okay. What do I mean by that? Here we are seeing that the application, whatever is there, the application for Jupyter Notebook is just a layer, is just an application inside the system that we are running called as pink. Okay. So for that application, right, for that particular application to be visible, right, we need to interface it with our system. So we need to make sure that we can interface the board, the Jupyter Notebook from the board to the system. How do we do that? Is you can open control panel. First thing is you can turn on the board, open your settings in Linux or control panel in Windows. Once you open that, you will be able to see one option for network settings. In Windows it is network and internet, in Linux it is only network, right. In Windows you have network and sharing, open that, network and sharing center. In Linux you will directly be able to see, okay, you will have one Ethernet connection there, okay, wired connection it will be called. Okay. So once you turn, sir, you need to turn on the board for it to work. Yeah, we need to have the LAN cable. So once you have that, you can open settings, open the wired settings. Yeah. Okay. In Windows also it's the same thing. You can open the Ethernet status. Inside that you will be able to see properties. Okay. Click on properties. So that is technically the settings. Okay. So once you are here, you need to open the IPv4 settings. Okay. In Windows it is IPv4 properties. Click on IPv4, there is a list of things, in that you have IPv4. Click on IPv4 and click properties. So everybody should be here by this point. You have option to change the IP address. So I have told you that we are using the Ethernet and the Jupyter Notebook is launching on the board. Inside that you will have network and sharing center, you have that, inside that you will have Ethernet connection. You will have two connections, ma'am, essentially. One is the Wi-Fi that you are connected to and the second is the Ethernet. If you have two Ethernets, you need Wi-Fi. Even without that you can do this setting, not a problem. You can give in the range of this IP. So what is happening right now is my board is a system, is going to act as a system of its own, okay, and I am trying to access an application on this board using something similar to an FTP server. Okay. So in order to use something like that, in order to use a server, you need to be in the range of that server, right. So we need to assign our Ethernet ID in the range of the board. So how do we do that? Is 192.168.2.1 all the way to 98. You can give any IP address. Okay, 192.168.2.1 to 98. You can give any IP address, no problem. 192.168.2.1 to 98. So by that time your board would have booted, you will be able to see all the LEDs glow. You can search for the IP address 192.168.2.99. Okay, you can click on a new notebook, and what you're seeing here, okay, is going to be called as a cell. Okay, this is called as a cell. Okay, the use of this particular cell is something similar to adding a breakpoint in C or C++ compilers. Okay, so if you want to have some intermediary outputs, you can use these cells. So there is a plus button at the top to add more cells. Okay, so either you can do your complete design in one single cell, run it at once, not a problem. If you want to add some kind of intermediaries, get some intermediary outputs, you can add more cells, and you can tell your program to print something or give the intermediary out. So I have a small program here. You can just enter this program, you can just type it in. You can do it in whichever fashion you want. You can directly put everything in one cell, or you can put it in multiple cells, not a problem. But you just make sure that you enter this particular program. So what I am doing here, what this particular program is doing is, I am importing the base overlay. Okay, the base overlay is again a .bit file. Okay, it is a pre-generated .bit file. It's called base.bit. I am just taking that bit file, and from the pink libraries, I am taking the LEDs. Okay, once I have both of these, I am writing a simple program to run the LED, to blink the LED using a toggle function.